So, welcome to the fourth module of surface characterization. I hope you have learned something in the first three, which we covered FTIR with ATR configuration. We also covered Raman spectroscopy, and then we covered a very important technique which is XPS, X-ray photoelectron spectroscopy. Now, my last part of surface characterization is something which you are very familiar with, is called scanning electron microscopy. And this is one technique which is very well known to everyone. It is very widely used by students and researchers everywhere, because these are like eyes to what is happening on the surface of the material. So, but I will give you some very simple aspects of it, how it can be useful to us, and if need be, we can actually look at how we can use it also for chemical analysis. So, when we come to chemical analysis, as you may all understand, that scanning electron microscopy is actually for surface morphology, looking at the morphology, how the surface features are. But there is something which is called EDS, which is called electron dispersive spectroscopy, and we can use this technique in combination with scanning electron microscopy to find the chemical information about our sample. And some of you may already be aware of this technique, but I will just explain you this along with the SEM. So, let us come to the slide and look at how a scanning electron microscope looks. So, in this slide what you can see is a geol. Let me select a pen from here. So, it is a geol system. So, I am not really promoting any, but because this machine is available in our lab, that is why I have taken an example of it. And it has something called a main part, which is this beam. This is the main this is the main instrument. This part of the instrument is the main instrument, and I will show you the various parts of it, and this is the electronics and the power supply of the instrument, and this is the control. So, this is the main analysis chamber. These are the electronics and power supply, and this is the control unit, and also we can look at the results here. So, this is how the instrument looks. So, let me now erase this thing and come to some specific parts. So, at the top of it is a electron gun. So, this is your column which is under high vacuum, and there is a electron emitting gun at the top. So, there are various kinds of guns, I will not go into those details, and this electron gun emits a electron beam. So, this blue colored, what is shown here is what is shown here in the blue color is the electron beam. So, electron gun emits electron beam, and it falls on a sample which is given in shown in red, and then where there the interaction happens. So, what we have is the electron gun, and then we have a sample, and on this sample the electron beam is impinging, and as it impinges, there certain things happen. As in the last technique in the XPS, what we saw, that X-ray beam was falling on the sample, and then electrons were getting emitted. Here electron beam is falling on the sample and electrons are emitting. So, which means that this electron beam, as it comes on to the sample, this electron beam is so powerful that it knocks out the secondary electrons, I mean secondary not to the sample, electrons from the sample. So, for example, if I want to draw it to you to explain. So, there is a electron which is coming onto the sample through electron beam, and this is my sample, and my sample also has electrons in the atoms. So, this electron will knock off a electron. So, this is what is happening, and this I am calling a primary beam, and this I am calling a secondary electron. Now, this primary beam is just the beam which we have created, and secondary electrons are coming from the surface. Now, they come only from the surface, this is very important. So, now if there is a morphological feature on the surface, so what may happen, you will have a detector here. As the electron beam comes, it strikes, so electrons are emitted. Now, depending on where the beam is striking, electrons may emit in that direction. So, if they are in the direction of the detector, they go in, if they are away from the detector, they do not go in or go less. So, depending on whether they are going more or less, there is a gray image which gets created. A gray image gets created, and this gray image will have bright or dark points. So, bright will show whether the sample has a feature which is coming up or a dark which is going down, depending on whether the electrons which are coming out are directed towards the detector or not. So, the feature, so what happens, let me tell you in slightly more detail. Let me select a different color pen. So, this is your sample, for example, and it has some features on it. As the electron beam comes, it focuses on a very small part, it looks at the feature at that point and it emits an electron. Then this gun moves to the next part and elects an electron, it moves to the next part, emits an electron, not an electron, many electrons, but I am just for simplicity going. So, what you do is you scan with the beam your sample from one point to another point to another point to another point to another point, and depending on whether it had a hill or a slope or a valley, either the electrons emitted will be more or less. So, by collecting on a detector, at one point the electrons may be more, so it is a bright spot. On other point, the hill is in such a way that the electrons which are coming are very less, so it becomes a dark point or a gray point. So, by that we can actually create a gray image which is representative of the morphology of the sample surface. So, this is how a scanning electron microscope works. So, we are interested in these secondary electrons. There are other detectors also in an electron microscope. I am not going to talk about it because this is not really a course in electron microscopy, that can take a very long time. I am only giving you the basic fundamental parts of it, so that it is something which can help you to initiate in this direction. Now, if we take a sample, say a carbon sample. So, this is my textile sample which is made mostly of carbon, hydrocarbons. So, carbon, oxygen, maybe nitrogen to some extent. So, this is something which does not have too many electrons, right. So, I will not get a very strong signal. Plus what happens, as these electrons they come and hit the sample, some of them stay on the sample and this sample will get charged. So, you will have a lot of negative charge on the sample. So, if this negative charge builds up with time, then the beam will not fall, the other electrons which are coming, they will start to repel, and if they start to repel, let me show you, it repels. So, I have all electrons. So, the next electron which is coming will get repelled, it will not reach the sample or it will get deviated. If this happens, then I will not be able to scan my sample. So, I need to remove these electrons from the samples, I need to remove them. And how do I remove them? If the sample is a hydrocarbon non-conducting sample, then it will not get removed. So, what I need to do is I need to put a layer of conducting material. So, I coat my textile or my material with something which is conducting. So, which can be say with this color. So, what I do is I make a very thin coating, evaporate say gold, platinum kind of materials or silver or maybe even carbon, and I deposit on the surface. Now, one has to make sure that if I have a features like this and I deposit a layer like like this, then obviously I have lost all the features. So, if I am looking at nanometer scale features, my coating has to be in angstroms only, then I can find those kinds of features, otherwise all those features will be lost. So, the coating machine has to be good and we have to control the thickness of the coating. The coating should be sufficient to make it conducting, but it should not be enough to mask my surface features. That is the first precaution we have to keep. So, once we coat these materials, we can take them inside the chamber, and we can actually, once we take them inside the chamber, we can impinge our electron beam and collect all the electrons to find the morphology which will come on the screen. Now, the finer is the beam, better would be the you can imagine I can really magnify the image. So, why are we using electron beam? Because electron beam has depending on the voltage, it has very low wavelength, and if the wavelength is low, we can really make a very large magnification. See, in a optical microscope, we are limited by the magnification because our wavelength of light is about 500 nanometers. So, as the principle goes, our thumb rule goes, that any feature which is less than 250 nanometers will not be visible by a light which is 500 nanometer, because it will not be able to interact with that kind of a feature. So, to find something which is of much smaller scale of 10 nanometer or 5 nanometer or 1 nanometer, I need wavelengths which are of that order, and light beams cannot have, the visible light beams cannot have that kind of wavelength. So, electron beam can have wavelengths whatever we want depending on the voltages we use to produce them. So, if we produce high voltage beams, then the wavelengths are so small that we can actually go to sub nanometer scales to see what is the feature. And in scanning electron microscope, we can easily look at 3, 4, 5 nanometer kind of features or 10 nanometers features if we have a good electron beam and a good instrument and we know how to operate it properly. So, we can look at these samples by coating them using either where I have written, either I can coat them with, make them conducting by gold, silver, platinum, I can use all these kind of elements, but the coating has to be thin enough than the features I am looking at. So, this is about the microscope. Now, there is another thing which happens once this electron beam hits the sample. Let me rub some of these things to make some space for you, so that we can now look at the other aspect, which is the EDS aspect of this simple system. So, if I have, let me rub this completely. So, when an electron beam hits the sample, let me take the pen again. So, my sample is there, it has carbon and it has orbitals around it and it has electrons. So, when an electron beam is coming and it hits these electrons and these electrons are emitted, then there is a space created. So, if I say remove this electron, then there is a space created, and what will happen is the electron from a higher orbital will jump to the lower orbital to fill the gap at the lower energy levels. Now, when this happens, some energy will get liberated, and this energy is in the form of X-rays, and these rays can then be detected. So, this is what I have shown you as orange, that as the electron beam hits the sample, secondary electrons are emitted, along with it, because of the transfer of electrons from higher orbitals to lower orbitals, because lower orbitals electrons have been removed. So, as they get removed, the electrons from higher orbitals. So, this was not removed, say lower one is removed. If higher one gets removed, there will be no X-ray, but if the lower orbital electrons are removed, then the energy difference between these two orbitals will get emitted in form of X-rays. Now, these X-rays is what I have shown you is in this is, so this is X-ray signal which is coming from the sample, and this X-ray I can detect using a EDS detector. So, I can just attach a EDS detector and these X-rays will get detected by this detector, and this detector let me go back, and this detector can tell me what kind of X-rays have come, what energy X-rays have come, and these energy X-rays are very specific to the differences in the orbitals energy levels of an atom. So, it will tell me whether that X-ray came from carbon. There may be many types of X-rays, because there are many electrons. So, there may be many transitions. Similarly, if it is a phosphorus, there may be many more electrons in phosphorus, and any one of them can come out, and then there will be transfer of electrons from other orbitals to that orbital, and there will be specific energies which will be liberated or emitted in form of X-rays, and these will be collected by the EDS detector. So, there will be combination of various signals, various X-rays which will be coming from one element, and by looking at those combination I can say whether it is coming from carbon or it is coming from nitrogen, it is coming from phosphorus or iron or silver, whatever it is, I will be able to detect that. And if I, because these are very specific to the atom, these differences of energy which is coming as X-ray are very specific to an atom. So, I can detect that atom. So, I can detect all the atoms which are present. So, if there is a carbon and hydrogen and oxygen present, hydrogen cannot be detected, but boron onwards all elements can be detected. So, nitrogen and carbon or oxygen which is present will be detected, and if I have added some material on my textile on the top of it, then that will also get detected, because it will also emit a signal from the surface. Now, but one problem will come if I have put say a silver finish on my textile or any other material which I have put on my textile, and then I have covered with silver or carbon or platinum or gold to make it conducting, then my signal from those materials will get lost, because I will have very strong signal from the coated material. So, what is normally done is when we take an EDS, we do not coat the samples. Our samples which may be non-conducting, but we do not coat them with such materials. If we have to go for higher magnification, then we have to coat them using carbon. So, if we take a carbon layer, then we know carbon signal will go up, but then all other element signals will not get masked easily. So, one has to be very careful that your coatings signals will also come. So, you should know what your coatings are and what your samples which you are trying to detect are. There should not be any overlap in that respect. So, what you see is a picture which I am showing here. It is a cotton fiber which has certain particles on it or some kind of actually layer of some resin, and you can see striations mark of the primary wall of the cotton. And then suppose you grow some nanomaterial on it, or you apply some nanomaterial using certain application techniques, then what can change is the same fiber at higher magnification. So, you look at the magnification, here the magnification is 5000 only, and here I have taken the magnification to 60,000 approximately. And what we have done is we are looking at now nanoparticles which have been deposited on these. So, these nanoparticles, very small and large chunks are also there. So, we know what kind of morphology it has created, and all these are particles, and these are all deposited on this cotton. So, this is without deposition, this is without no deposition, and here there is a deposition. So, one can look at the scanning electron microscopy pictures to see whether the changes have taken place what we wanted, whether the changes on the surface of the fiber or of the textile has happened as we want or not. And suppose we wash it, and then we can look at whether the particles remain or the particles have changed or less are there or same are there, then we can say wash durability, whether it is there for our finish which we have created on a textile material. So, this is something which is very interesting, because it is like eyes to our modifications which we have done on the textile. If we look at under microscope, a light microscope, we will not be able to detect anything in that level. If you do nanomaterial kind of modifications, nano technology based modifications, we will not be able to see anything. Even if you want to put a very fine film of resins, microscope will not show anything, but a electron microscope will show you create a proper film onto the surface. You can take cross sections of fibers, you can look at the cross section of it. You can, if you is a layered or laminates material, you can take a cross section of laminates and make sure that the edge is facing upwards towards the electron beam, and then you can look at and analyze the depth of various layers in a laminate, whether they are bonded properly, they are fused or not fused, or how they are looking at each other. So, even inside morphology can be looked at once you cut the sample, or if you have a say a composite and you want to break the composite. So, normally one of the technique which is used is you take it into a liquid nitrogen bath, you freeze it and then you just fracture it. So, it becomes rigid and then it just fractures, and you fracture a cross section and then you take this cross section inside a scanning electron microscope and look at what is there inside the sample. If you added something, whether how the fibers are, how the resins are, how the matrix is, you can look at various aspects of. If you have added some kind of a reinforcing material or a nanomaterial, then you can even look at them. But at times if they are not creating any different morphology, then you will not be able to detect. You will be able to detect it only if there is a morphological change, because it is looking at only on the surface. So, even cracked surface, it is only looking at the surface, it is not looking inside the material, right. So, this is something which we have to keep in mind, but one can look at the morphology very carefully. Then EDS is also called EDX, the mapping. You can actually do mapping. So, you have a surface, for example, let me choose a pen here. So, you have a surface of your sample and you have really amplified it in SEM. So, EDX actually works in combination with SEM. So, EDX can work as a area snap. So, in a sample it can take a area, a big area as the material. Let me just take a pen. So, you can choose it as an area scan, not a scan, but a area signal, and it takes average of everything which is present in this spot or in this area. And so, there will be carbon, nitrogen, phosphorus, whatever elements are present, they all will be detected. Or what you can do alternately, you need not take the area a bigger area, you can take a small focused light of your scan electron microscope, and what you can do is you can point it, scan it from point to point, from one point to another point, from one point to another point, and at every spot you can take an EDX spectra. So, what will happen? You will know what is present here, you will know what is present here, and how the chemical nature is changing. So, you can actually do a mapping. This is called mapping. So, if for here, for example, we have done a mapping of a cotton fabric which is treated with P25 titania. P25 is a trade name for titanium which is commercially available, nano titania which is commercially available of size 25 nanometer. So, here this is a electron image. Let me laser point. So, this is an electron image and you can see fibers, cotton fibers, you can see the convolutions, and on that fiber are small dots like structure. These are morphological changes which have happened because of the deposition of titania. So, P25 titania is deposited on the fibers. We can see all these small particles. So, we can see we have done something. Now, how do we say or tell anyone that these are titania? It may be say anything, no. So, what we have done is we have done mapping of 3 elements. So, we have done mapping of carbon, we have done mapping of oxygen, and we have done mapping of titania. So, obviously, my cotton fiber has carbon as well as oxygen, and see this is a K alpha 1 and K alpha 1. This is a specific transition peaks from EDS. So, and then we have taken titania as well. So, you can see as expected lot of red is there now. So, obviously, surfaces which are exposed to the electron beam in the right direction are bright. Sorry, let me go for back to my slide, and the areas which are darker are away from the detector. So, they are appearing darker. So, in this case they are valleys. So, electrons are not coming out from that. So, most of the places you see red, filled red. So, it is all carbon and so is the oxygen, because cotton has both carbon and oxygen. So, here we have chosen a color green to detect to represent oxygen, and in this case red for carbon, and then we have used blue for titania, and you can see even titania is present all over, although the density of titania is not that strong as carbon and oxygen. So, we can see, and this is all done at 10 micrometer scale. So, this much scale is only 10 micrometer. So, it is quite enlarged picture, but you can go even higher magnification if your EDS detector is good. Good EDS detector means more sensitive with more area of detection, but in this case we have been able to show that it is uniformly present on the sample. So, this is how EDX mapping can help us to find the surface chemistry of a sample. But please keep in mind that in EDS detection it is not just the surface, it is not like XPS. In XPS we were looking at hundreds of nanometers only. Here we are looking at microns, we are not looking at just the top surface. So, we are looking at SEM surface morphology is the top surface morphology, there is no problem there, but when we are using EDS, energy dispersive spectrometry, then the signal, the X-rays which are being collected by this detector are not just from the surface, but also from the depth of the sample. And it has been said that it can take a couple of microns inside, maybe more than that, at least 1 or 2 microns, because electrons can have an effect and they can penetrate a sample to some depth, and then X-rays can be emitted from elements present inside the surface. So, the EDX mapping which you get is not from the surface, but from the top say 500 to 1 micron depth of the sample. So, though you get most of the signal is still from the surface. So, if your surface has 100 200 nanometer layer and then you will get a very strong signal from the surface, but anyway the surface will be more active, it will give you more information, signal will be much higher from the surface and will be much lesser from the underneath layers, but it will be there. So, the composition which you will get from EDS will contain both the surface and part of the bulk, part of the under layers. So, one must be a little critical in saying the quantitative values. So, in EDS it gives you not only the peaks of what elements are present, but it also tells you the percentage, the weight percentage or atomic percentage of material present in the analyzed area. So, one may have a urge to say, yeah, this is my surfaces, but no, it may be surface as well as part of the inner layers or under layers of the surface. So, if the surface is if the material is homogeneous from the surface to the bulk, then it represents the composition of the sample, but if the surface is different from the bulk, then it is a representation of mixture of the surface and the bulk. That is something which we need to keep in mind. So, with this I come to the end of my lecture on EDS combined with SEM. EDS, for EDS we have to have an electron gun source. So, it is actually cannot be done independently, it has to be combined with an instrument and especially in SEM is very useful, or in TEM it can be used in the similar manner, which is transmission electron microscopy, but that we are not covering because that is not part of our syllabus in this module. So, thank you very much. I hope this module will also would have given you some information about how you can use electron microscopy and EDS for carrying out surface analysis as well as to some extent bulk analysis using both the techniques. So, thank you very much. We look forward to your comments and reactions. Thank you very much.